All right, so we're going to look at what happens now when you write down the Euler-Lagrange equations under a change of coordinates. Okay. And so what I mean by that really is that if you have a manifold, right, and you have two overlapping charts, okay, so let's just say you have one chart here with open set U, and another chart that's like which is defined on an open set U tilde, and there's an overlapping region, and you write down essentially two local coordinate systems. Okay. And there is a overlap region in the two charts. And you want to see basically, well, it's like when you are in the overlap region, it's like, and you write down the equations in one of the charts versus the other, whether these two sets of Euler-Lagrange equations are equivalent, which is to say that if it's satisfied in one chart, it's also automatically satisfied in the other chart. Okay, so so I have a configuration manifold Q, right? So let Q be a configuration manifold. With coordinates, let's call that Q1 to Qn, and sort of Q1 tilde to Qn tilde. Okay. For Q with overlapping charts. Okay. So you have two charts where the second one is denoted by the tilde. Okay, and so what we want to see is, or you want to show is that if L is a Lagrangian on Q, right, then the claim is the following, that when you write down the sort of the term which vanishes in the Euler-Lagrange equations, right, which is d dt dl dv tilde I minus dl dq tilde I, right, that is related, it's like to the expression in the other coordinate chart in the following way. So this is equal to dqj dq tilde I, right, times the following, right, d dt dl dvj minus dl dqj. All right, so more or less it's like what that means is that since this thing here is the Jacobian of the change of coordinates map, which is, I mean, the change coordinates map is always invertible, so this Jacobian is non-singular. So essentially what that means is that when the left-hand side is is 0, right, that implies this term in the parentheses, which corresponds to the Euler-Lagrange equations in the other coordinate system, is also 0. So more or less, it's like this tells you that if the Euler-Lagrange equations are satisfied in one coordinate system, they will be satisfied in the other coordinate system as well, which is, of course, what you want. And perhaps not so surprising, right, because Hamilton's principle is in some sense coordinate independent, and so you should expect that the resulting stationarity conditions, which are the Euler-Lagrange equations, should have some notion of equivalence irrespective of the choice of chart you choose. Okay, and so that's more or less what happens. Okay, so this is saying that if the Euler-Lagrange equations are satisfied in one of the coordinates, or let me rephrase that. So the Euler-Lagrange equations are satisfied in these coordinates if and only if the Euler-Lagrange equations are satisfied in the other coordinates. Okay, so this notion of satisfying the Euler-Lagrange equations is independent of the choice of coordinates, which is of course exactly what you would expect just from the coordinate-independent way we framed Hamilton's principle. Okay, so let's see how you show this. So much of this, of course, is just a consequence of the chain rule, if you will. Okay, so we have the following. We have that the change of coordinates for the it's like of the positions. It's like sort of, or the Jacobian. It's like for the change of coordinates of the position. It's like is the same as the Jacobian of the change of coordinates for the velocities as well. Okay, so we have that dv dj, the v tilde di is equal to dq dj, or dq, it's like j, dq tilde I. Okay, so the vj, the v tilde I is equal to dqj, dq tilde I. And the other thing is that the vj, the q tilde I is equal to d squared qj, right, d q tilde I, d q tilde k, contracted into v tilde k. All right, so these are just sort of some basic observations. Then by the chain rule, we have that dl d v tilde I is equal to dl d vj, right, d vj d v tilde I, right, plus dl d qj d qj d v tilde I. Okay. And this is going to be equal to, okay, so this term here, right, is going to be replaced with dqj dq tilde I, and then this term here is going to vanish, all right? So this is equal to dl dvj dqj dq tilde I. Okay, and then dl dq tilde I is equal to dl dvj dvj dq tilde I plus dl dqj dqj dq tilde I. Okay, so this is equal to dl dvj, and then d squared qj dq tilde I dq tilde j, k, I'm sorry, okay, k v tilde k plus dl dqj dqj dq tilde I. Okay, so once you have that, it's like you also make the observation that the time derivative d dt of dl dv tilde I is equal to the time derivative of dl dvj multiplied by dqj dq tilde I. So this is just the product rule, right? So I'm taking the total time derivative of this thing, and I'm using the product rule, right? Plus dl dvj, all right? And then what happens is that I'm taking the time derivative of this term, which is then dvj dq tilde I, which is this term here. Okay, so I have a d squared qj dq tilde I dq tilde k v tilde k. Okay. All right. So I can subtract, it's like this, right, from this, and then see what I get. So d dt of dl dv tilde I minus dl dq tilde I is equal to the equation which I wanted to have, right, which is that dqj dq tilde I ddt dl dvj minus dl dq j. Okay, all right, so let's just see how you get that, right, because there's this dqj dq tilde j term, which I've pulled out here, and then there's a ddt dl dvj term, which is here. Okay, this term cancels out with this term here, so that disappears, and then you're left with this term, and again the qjq, so dqj dq tilde I term, right, gets pulled out, and then you're left with a dl dqj term, which shows up here. All right, so so that shows you what you need, and then the other observation is that this thing viewed as a matrix, right? So dqj dq tilde I, right, for I and j, right, is invertible because it is just the Jacobian of the change of coordinates map. And then by sort of the assumptions, it's like for a chart that has to be invertible because more or less it's the composition of the inverse coordinate chart with another coordinate chart, right? Okay, so this implies the equivalence of the Euler-Lagrange equations in the two coordinate charts. All right, and so again, this is what you would expect, right? So you would expect that every time the Euler-Lagrange equations are satisfied in one coordinate system, then they should be satisfied in another coordinate system where the two coordinate systems have an overlapping region and they're part of an atlas, it's like for the manifold. Okay, so again, this is not so surprising, but it's still helpful to explicitly check this just at least once, all right?